The past is very interesting. It's how we got here. The very early part of the radiation-dominated era will occupy us a lot, but before we go on, it might be nice to say something about the future. What do our models predict for the future? Well, we said what we predict for the future is domination by the cosmological term, since we found that it is non-zero. We are already living in a period, in an epoch, where the cosmological density of dark energy, or the cosmological term, is larger than either radiation or dust. And over time, as the universe expands and both dust and radiation are diluted, the cosmological constant, or the cosmological term, will become more and more important. So if we have a universe in which the only form of energy density is in the form of dark energy, this is not diluted at all. This means the ratio of A dot to A, the Hubble constant, is in fact a constant, because the right-hand side of Friedmann's equation becomes time-independent. A function for whom the ratio of its rate of change to the function itself is constant is an exponential function. And indeed, in a period dominated by the cosmological term or by dark energy, the behavior of the scale factor is not the power law with power less than 1, square root of t, or the 2/3 power of t. Rather, it is an exponential dependence on t, and this has many interesting aspects. This represents an accelerating expansion, a runaway exponential, with a constant value of h that is independent of time, a dot over a. The left-hand side of the Friedmann equation is now a constant because the right-hand side is a constant. And we observe this, remember, here at about 0.7 was the transition from the dust-dominated decelerating expansion to the accelerating, tending to exponential expansion, dominated increasingly by dark energy, that is the future of our universe. So this exponential accelerating expansion is what we predict for the future, given the cosmological data that I have provided. Now, what does such an exponential behavior describe? Well, one way to think about what this means is to remember that the speed with which photons move is the speed of light. But if we measure the distance in today's universe that a photon will cover, in other words, if a photon takes a time t to get from one galaxy to the next, to some other galaxy, how far are those galaxies today? We find that the coordinate speed of a photon, we said, was c over a of t, which means in terms of making it from one galaxy to the next in today's galaxies, the speed of a photon is, in the exponentially expanding universe, exponentially attenuated. The speed of a photon is attenuated in this sense in any expanding universe because a of t is growing, but the exponential growth is different from the power law growth. It's different in the sense that if a of t is proportional to some power less than 1 of t, then as t becomes large, the distance a photon covers becomes infinite. In other words, a photon can traverse any distance. If you wait long enough, a photon will get from any galaxy to any other galaxy in a radiation-dominated world or in a dust-dominated world. However, in a cosmological term or dark energy-dominated world, a photon will not. The total distance that a photon covers, if its speed is attenuated exponentially, becomes finite. Even if you wait forever, a photon will not get as far as you want it to get, and this will have profound implications for the future. Before we move on, I want to point out another interesting property, another interesting way in which this exponential behavior of the scale factor differs from the power law behavior that we found in the dust-dominated or radiation-dominated eras. In our universe, of course, prior to about 8 billion years after the Big Bang, the universe was dominated by dust, so we don't see the exponential. But if we actually were to plot a purely exponential, a purely lambda-dominated universe, then it would always be exponential, and the exponential is very different from the power law in the past, in that the exponential asymptotes as t becomes very large and negative to 0, but never gets there. A universe which is dominated by a cosmological constant will have existed forever, and there will not have been a finite time singularity or a finite time Big Bang. Yes, far enough into the past, things would have become very dense, but it would be very far into the past, and if the universe continued somehow mysteriously. Of course, a universe which had any matter or radiation in it, like ours did, well, at some point in the past, as whatever radiation we have today was more concentrated in the past, it would eventually take over from the cosmological term. But if somehow we had a universe dominated by a cosmological term, then that's an eternal universe. That is a universe that need not have a singularity. Curvatures do not become infinite in the finite past, and this might be of interest in the next week of the class. For now, we're going to use the fact that we know something about the future to discuss two important issues, some of which we've already touched on. So, one question which grows out of what I've just been talking about is, how far can we see? Well, of course, the farthest we can, in principle, really see is the surface of last scattering, the universe at 380 billion years, and 380,000 years old. And we've seen that. But in principle, we can't see with light farther, but can causal effects propagate to us farther? In other words, what is our light cone? What is the past light cone? What is the collection of all events in the history of the universe that could have influenced us today? And how does that cone grow as time goes by? So in a flat universe, for example, your past light cone is just the region between those two diagonal light rays that we used to draw. If you go far enough into the past, it eventually includes any point in the universe. Eventually is in your light cone. If the point is far, it can only influence you from the dim past. But if you go far enough into the past, you will eventually, all parts of space fall in to your light cone far enough into the past. This is not true in a universe with a finite age like ours, and so we expect that the size of the region that can causally influence us is finite. Only a finite part of the universe is within our past light cone, if only because the universe has existed for a finite time. Now you have to do a calculation. The size of what we call the observable universe, again, it's not necessarily what you can see with a telescope, but what causally could have influenced you, is called the particle horizon. This consists of all those objects which we see as, if we could see them, as they were at t equals 0. And notice that the difference between 380,000 and 0 on a scale of billions of years is going to be hard to determine. So, how does this depend on time? Well, because of the slowing expansion in both the radiation and the matter era. If you wait long enough, I said a photon will go from any point to any point. So if you wait long enough, you will eventually see the entire universe. This is reflected in the fact that the size of the distance from you to your particle horizon in the radiation era grows with t, and in fact is given by twice ct. This means that when the universe was a year old, you could, if you could see all the way back to the Big Bang, you could see things that are 2 light years away. Wait, but the universe is only a year old? Yes, these things are now 2 light years away. Remember, the universe has expanded them since the light left them that has just got to you at the ripe old age of a year. Likewise, in the matter era, because of the different behavior of the scale factor, the horizon again grows with t, but it's the dependence is a little bit different. You can see all the way out to a distance of 3 ct. So in the dust-dominated universe at 8 billion years old, you could see 24 billion light years away. Notice, much more than 8 billion years, all the way out to 24, or if it was 8.8, all the way out to almost 27 billion light years away. Today, we can see a little bit farther. Today, at the ripe old age of 13.7 billion years, we can see all the way out to 46 billion light years. Now, we don't quite see that far because we can only see as far as the cosmic microwave background, but that's pretty close. Now, over time, can we see more and more? Does our past light cone grow? It grows, but remember that in the exponential expansion that will dominate the future of our universe, it will cease to grow because the coordinate speed of a photon is exponential and the maximum distance a photon can travel turns out to be finite. And indeed, the horizon distance grows, but it doesn't grow without limit. It becomes, well, it grows with the growth of the universe, but in terms of including more and more galaxies, it stops including more and more galaxies. Anything that is today more than 62 billion light years from us, we will never see. and will never come into our past light cone, and if something happens there, it will never influence us. So our total observable universe is today a sphere of radius 62 billion light years around us, and all the stuff that is in it is all the stuff we will ever see. So for example, if our universe were to be somehow closed and a big loop of 3 trillion light years would bring you back here, not only would we not have known it yet, but perhaps we have no way to know it in principle, because the expansion is the exponential expansion will render it invisible to us forever. So here's a figure that that describes this. So the dashed line here is our particle horizon. Here, time in billions of years from the Big Bang. The present is marked by this horizontal line in the middle of the graph. And here we see our past light cone, all of the events that could have influenced us, and we see that all of the events that could have influenced us are objects that lie all the way out to about 46 billion light years away from us. That's if we could see all the way out to the beginning, to the Big Bang. Of course, we don't see back to the Big Bang. There's a cutoff. It's hard to distinguish on this scale just before the Big Bang at the surface of last scattering on actual seeing. And as time goes on, we will see farther and farther into the universe. But you see that even if we wait forever, the farthest we will see is, as I said, about 60 billion light years. And this is the light cone of an observer where we are at time infinity. This is all we will ever see. And as a function of time, if you ask, where in the universe have we been able to see? Well, of course, at time 0, we couldn't see anything because no photons had no time to get anywhere. And over time, we see more and more of the universe, and it will stop when it hits that number of on the order of 62 billion light years. So here, distances are drawn in terms of today's distance, and so co-moving observers or galaxies move along vertical lines. A galaxy that is 40 billion light years away from us will have become visible to us just recently. And so only recently have we been able to see what happened 40 billion light years away at about the time of the Big Bang. This is our particle horizon. And this is the answer to the question, how much of the universe can we see? What can influence us from the past? What is our past light cone? You can ask a more interesting question, perhaps, which is, if we look at today's universe and something happens, how much of that can we see? Well, of course, we can't see any of it today unless it happens here because it takes time for light to get here. But if we wait long enough, how far into the universe will our past light, into today's universe, will our past light cone extend if we wait long enough? This is what is called the event horizon. So the event horizon is a line that separates events from which light will reach us someday from those that we will never see. Remember that all of the things that happen outside at a distance larger than 60 billion light years, we will never see. We know we will never see them. We'll never see them all the way back to the Big Bang. So even if we live forever, we will never even see the beginning of time at those distances. But it turns out that this line over here, which is sort of the light cone of our t equals infinity event, does not reach through to the entire universe. As I said, it stops at 60 billion 2 billion light years at the Big Bang. But more interestingly, if you ask, say there is a galaxy 3 billion light years from us today, so that's this galaxy over here, we could see it at the time of the Big Bang, and today we can see it all the way to, a billion years after the Big Bang, or 2 billion years after the Big Bang. But if something were to happen there today, we would never see it. The number of things which we can see from any given time, and one way to think about it is, suppose that we want to exchange messages with somebody in the universe. Well, we can exchange messages at the speed of light, but we need a message to get to them sometime in the future, and then get back here. Well, we could have sent a message, since we can see this galaxy at the time of the Big Bang. If we sent a message at the time of the Big Bang, it would have arrived at this galaxy about here, and they could have communicated back. But if we send a message back, or if they send a message back to us now, it will never, ever get to us. So, if you notice, the vertical lines are leaving. The event horizon narrows into the future. So into the future we see less and less of the universe. If you ask at any given time, how much of the universe is still able to interact with us, it's this fraction. And this chunk is shrinking. It started out as 62 billion light years in either direction, will eventually be seen. And now, today, it's on the order of about 12 billion light years. So we will only ever see anything again if it is not more than 12 billion light years away from us. And in the future, this asymptotically becomes very small. And so in the distant future, the next galaxy cluster over, remember, our galaxy is gravitationally bound, it's not expanding. But the next galaxy cluster outside our cluster will become so distant that we will never see it. This, in fact, is the most sophisticated answer to Olber's question, or which Olbers, as we know, did not phrase. He just gave an incorrect answer to it. But Poe gave the right answer. The reason the sky is not infinitely bright is because we only see a finite segment of the universe at any given time, and in fact, that segment of the universe is narrowing, and so when you did that infinite sum of constant terms that added up to infinity, when you computed the surface brightness of the sky, that sum in fact terminates. Now, that means that there are objects behind our event horizon. There are events we will never see. So as this galaxy, we could watch this galaxy, and we would see it, and then it would blink out of existence when it crossed the event horizon. No, not quite. What would happen, of course, is that objects at the event horizon, remember that we will see this galaxy at this time here, and at this time we'll see the galaxy here, and notice that the intervals here are growing. This galaxy is becoming increasingly redshifted as we see it, and as it approaches the event horizon, the redshift becomes infinite, so the objects do not blink out of existence when they hit the event horizon. Rather, their radiation is redshifted and they dim to the point where they're imperceptible, and we of course never see anything cross our event horizon. This is very similar to the way that we never see anything cross the event horizon of a black hole. That is why we use the same terminology for both structures.